Hello, good morning everyone. Let us introduce ourselves. My name is Rochelle and I am a computer engineering major.
Arvin Nikam, electrical engineering.
Roberto Gomez, computer engineering.
James Wilson, electrical engineering.
Duke Nguyen, electrical engineering.
Priscilla Moreno, electrical engineering.
And we are Team Automouse. So our goal this semester was to create a micromouse that is somewhat fast yet still reliable. But what exactly is a micromouse? A micromouse is essentially a robot that can navigate to the center of a maze without any form of remote control. Our robot must conform to the IEEE Region 6 Southwest Area Competition rules. Basically, we will be given 10 minutes to map out and solve a 16 by 16 maze. Our robot must also be no more than $500 in total cost. The winner of a competition is determined based off of the time it takes a robot to get to the center of a maze. And here is Arvin, who will talk to you about the physical design of our robot.
Hello everyone. The first step in our project was to choose components. The first component was motor. We had the option of DC motor and stepper motor. We chose stepper motor because of the precision, and to compete with the other things that they had a DC motor, we chose a bigger size of the stepper motor to give us more torque and definitely more speed and velocity. So we chose a bipolar stepper motor with 36 torque. Then the motor driver used two more drivers, 32 microstepping. For the sensors, we used the sharp infrared proximity sensors, 3 of them, 2 on the sides with a short range, and the front one, longer range, of course, because when we go straight, we need to detect all obstacles ahead or the wall. The battery, we use 11.1 lithium polymer battery that give us enough power to run all the components. The brain of the micromouse microcontroller, we use 32 STM Discovery board. The biggest problem when you're using a large stepper motor is how you're gonna reduce the size of the mouse that be able to cruise around the mouse, around the maze, and easy to maneuver in the maze. So we placed the motor in the center of the chassis to give us more turning radius. And as you see in the right side, we have enough room all around the cell to go around, make a U-turn 90 degree or whatever. Then all the 3 sensors will be found. And the battery on the back. So we had to use the upper deck, and that is the completed prototype that we already have. More drivers and the microcontroller on the top, and switches and LEDs. And next is a video of mouse going around the maze.
This battery fell out. Well, it's like this parachute, you know? Yeah.
And here's Duke, he's going to talk about the system design.
Hello.
Hello, I would like to explain how we came up with this design. So in the middle of the screen, there's a big green block. There's a SDM microcontroller, which provides us useful peripheral like GPIO, timer, HCD converter, and user. So on the both sides, there's a pink blocks represent the motor driver. So to enable the motor driver, we need to connect to the user GPIO, and we also use two timer 2 and timer 3 to generate a required frequency for driving the motor. And on top of the microcontroller, there are 3 yellow blocks represent a sensor. So these sensors operate at 5 volt. So we need to use a LM7805 voltage regulator to generate from the input voltage, which is 11.1 from the battery, to obtain the 5 volt at the output voltage to avoid damage the sensor from burning them or damaging. And we also need 3 volt to turn on the GPIO of the microcontroller. And we also, for user interface, we use switches, which for turning on the disconnect or connect the battery and switching the mode from between mapping and maze solving. And we also use LED to indicate the interaction of the switches. And next, I would like to introduce Priscilla, who will talk about motor and driver in more detail.
Well, two of the most important features in this project are speed and control. We needed a motor to be powerful, fast, stable, and easy to maintain. That's why we chose a bipolar stepper motor. This device converts digital pulses into mechanical shaft rotation. These pulses are converted into current that travels to the winding, creating a magnetic force which makes the shaft to start rotating at a certain angle. This is called a step. We can appreciate this process in the animation for a full step mode at an 80-degree angle. Well, these motors can operate at 200 steps per revolution for a full step mode. We are using a 32 microstepping mode using our drivers, which can provide us around 1,600 microsteps per revolution for the motor. This will help us so the motor can travel smoother at higher frequencies. Since frequency manipulates the speed, we are using 6 kilohertz for the robot, so it's able to travel around the maze at a speed of 23.6 centimeters per second. Since the speed it's important, but we need to know what's around the robot. We are implementing special sensors, which James is going to talk about.
All right, so for our robot, we decided to use sharp eye proximity sensors. What these sensors do is they detect the proximity of the walls around our robot. We have 2 on the sides and 1 in front. How they work exactly is through infrared triangulation, as you can see in the picture on the right. The sensor fires out an infrared beam of light towards our surface. In this case, it's going to be a wall. It's reflected back to the receiver of our sensor, where it creates an angle. The larger the angle, the further away the sensor is from the object, and the lower the output voltage. This output voltage is then sent to our analog to digital converter of our microcontroller, where we can use that data to tell our robot to either stop, turn, or correct itself within the maze. We decided to use infrared sensors as opposed to other types of sensors, such as ultrasonic, because we knew that the maze was going to be held inside, where we don't have to deal with infrared noise from other sources, such as the sun or major light sources, as well as the fact that if we used an ultrasonic sensor, where they're based around sound, noise is a constant factor, and we also have to worry about the sensors cross-talking with each other, interfering with their own sounds. With the hardware out of the way, we would like to discuss the software of our design, and I'm going to pass it off to Roberto for that part.
Thank you, James. So in order to manage all our software, we decided to organize it using a state machine. Using this structure, we can clearly define all the possible actions that our robot can perform, as well as the transitions between them. The main tasks that our robot will be performing are mapping and solving. In the mapping portion, the robot will traverse the maze and find the shortest path to the center of the maze. Once it has completed mapping, it will return to the starting cell where we'll switch it into the solving mode via a switch. In the solving mode, the robot will once again quickly run to or drive to the center of the maze using the path just determined from the mapping portion. And this is the speed run. This is the official time that will be recorded for our competition. So exactly how does a robot perform the mapping? Well, we use an algorithm called flood fill. This algorithm enables the robot to keep track of itself in the maze and intelligently traverse it. So when the robot is initialized, it allocates a number in each cell which corresponds to the distance to the center of the maze. In this diagram, the black lines indicate known walls, and the gray lines indicate unknown walls to the robot. Prior to mapping, the robot assumes that there are no walls in the middle of the maze. When the robot enters a new cell, it performs several tasks. First, it updates the walls around it. Next, it updates the distance values depending on the newly discovered walls. And lastly, it determines the next cell to maneuver to by following the distance values in descending order. Using this method, we can, the robot can find the shortest path to the center of the maze. Now I'm going to pass it over to Duke, who will discuss our milestones.
Thank you, Roberto. So the milestones are the guidelines that help us to complete this project. So in October, we built the final chassis with a 2-layer that hold the driver and motor using brackets. And in early November, we coordinated the motor to set the mount, to navigate the mount to go straight, accelerate and decelerate, and to make turns in the maze without crashing to the walls. And in the middle of November, we assemble all the required electrical components and devices onto the PCB. And in the 4th week of November, we implemented the flood fill algorithm into the mouse to apply mapping and maze solving. And by December, we had our complete robot that was able to navigate, to move around the maze, and can solve the maze in the fastest, with the fastest speed and within the required time. And I would like to talk about the budget, so here's James.
All right, so for our project, we were allotted $600 total to complete it. And after everything was said and done, we completed the project with $400, $200 under budget. As you can see from the chart up here, most of our costs went to the hardware section, 35% and $140 total, followed closely by our batteries and power supply, which totaled around $87. And with that, we'd like to conclude.
And then that concludes our presentation. We would like to invite all of you to Design Day on Friday the 5th and to the competition on the 4th, which will be held in senior design. And we would like to thank John, Mark, and Dr. Tamala for mentoring and helping us, and the SDSU Electrical and Computer Engineering Department for sponsoring us. And last but not least, we would like to thank all of you for being here today. Thank you.